Okay, hello and welcome back to Chemistry Talk. Today I'll be starting a long series on acids, bases, and salts. There's a lot to do with acids and bases in general chemistry. Today is going to be an introduction to what they are, a little bit about them, but no math, just basically talking about, properties of acids and bases. And before I begin, be sure to subscribe to my channel so you get notified when I post new content, which is quite often. And you can also comment, ask me any questions. If you need help with anything, any special requests for topics, just let me know. Just comment and subscribe. So, the physical properties of acids and bases. So, the real important physical property of acids in the lab is that they turn litmus red. A base will turn litmus blue, and I'll get into what litmus is in a second. But in general, acids have a tart or a sour taste. Not to say that if you want to determine whether something's an acid or a base in the lab that you would taste it. You really shouldn't. But for example, lemon juice is very acidic. It's tart and sour, so that's a property of an acid. While a base is has more of a bitter taste. It's very slippery and and soapy. Most soaps are bases, but please do not taste these in a lab. Now, what is litmus? Litmus is a paper. It's a very small strip of paper. I'll highlight it here. It's a little strip of paper, probably about, I would say, the length of your thumb. It's a very thin piece of paper, and it's an indicator of whether a solution is acidic, basic, or neutral. If you put litmus into an acidic solution, it's going to turn red, as indicated in this first one. If you put litmus into a basic solution, it's going to turn blue. And if you put litmus into what we call a neutral solution, meaning it's not acidic or basic, it's going to either stay the same or turn slightly green. So litmus is a good indicator of the pH. Now, if you're really getting involved with acids and bases, which I'll get into in other videos, litmus is not the best way to determine whether something is acidic or basic, but it is a pretty simple way to get a reading. So there are lists of acids and bases. There are strong acids, weak acids, strong bases, and weak bases. Now, I recommend that you memorize the list of strong acids because most acids are weak. And what I mean by weak is that they don't dissociate 100%. Strong acids, which is this list right here, dissociate 100%. They're strong electrolytes. So the list of strong acids, there's really six main strong acids, and that's perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. So these are your strong acids. They're going to dissociate 100%, meaning you'll have an arrow that looks like this. You won't have an equilibrium arrow because they dissociate 100%. So like I said, most acids are weak. So if you see any acid that's not one of these six, it's a weak acid, and you know that it doesn't dissociate 100%. Now, we can classify acids as monoprotic or diprotic. This just has to do with the hydrogen ion concentration, because as I'll get into other videos, acids are defined by their hydrogen ion concentration. So hydrochloric acid is a monoprotic acid. It has 1 mole of hydrogen per every mole of acid. Meanwhile, sulfuric acid is a diprotic acid. It has 2 moles of hydrogen per 1 mole of the acid. Now, weak acids or weak electrolytes, they partially ionize. So, meaning when you write the dissociation of a weak acid, you need to include the equilibrium symbol, whether it's that single arrow or it's the arrow going in two directions, you need to include this. That symbolizes that it's partially ionizing, it's not fully dissociating. So, most acids are weak. A few examples are acetic acid, formic acid, hydrofluoric acid, carbonic acid, and phosphoric acid. However, there are many, 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 many more weak acids that partially ionize. That's why I recommend that you just know your six strong acids. That way, you know everything else is just a weak acid. Now, here I have included the dissociation of acetic acid. Now, I've done it two ways. One, I've included water in the dissociation, and the other one I haven't. You don't have to include water when you're writing the dissociation of weak acids. If you include water, on your product side, you won't get hydrogen ions. You'll get what we call the hydronium ion. And that's what this is right here, H3O plus. That's the hydronium ion. But hydronium ion in acid-base chemistry is the same as hydrogen ion. So if you're writing the dissociation of acetic acid, you don't have to include water because you'll just get your hydrogen ion here. And that would be your symbol that it partially ionizes. But if you want to include water, you can, but just know that you're not going to get the hydrogen ion, you're going to get the hydronium ion. And that is the same thing as the hydrogen ion. Well, we'll get into another video why acids lose a hydrogen ion, but that's just how they ionize. So once again, you don't have to include water in the dissociation of weak acids. However, that is not true for bases. So most bases are strong. They dissociate 100%. So this is a few list of bases. If you notice, all of them have this hydroxide ion, and the hydroxide ion is OH minus. That is our indication of whether something is a base. We look at the hydroxide ion concentration. So if you look here, there's a few examples: sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, aluminum hydroxide. It goes on and on. Most bases are strong, meaning when you write the dissociation, they're going to dissociate 100%. You include your single arrow because they're not going to shift back and forth. They dissociate 100%. However, there are a few weak bases, very few, but there are a few. The most common is ammonia. This is your most common weak base. A couple other weak bases, codeine, hydrazine, I can't think of another. But a lot of painkillers and narcotics are weak bases. Morphine is what I was thinking of. Morphine is another weak base. Now, let's talk about the dissociation of weak bases right here. I said you must include water in the dissociation of a weak base, and here's why. One, notice I have the equilibrium sign. That's symbolizing that it doesn't dissociate 100%. It's a weak base. But the definition of a base has to do with the hydroxide group. And if I was just to dissociate this base, a weak base, without water, I wouldn't end up with a hydroxide group on the product side, which would mean something is weird and it's written incorrectly. I would just have NH4, which is ammonia's conjugate base. That's conjugate acid, but that's different. But you would not end up with the hydroxide ion, which you need. So by including water, that's how you get the hydroxide ion. So you must include water when writing the dissociation of weak bases. Last thing to touch on in the properties of acids and bases is the pH concept. Now, pH doesn't have any units. It's just a number. You can either have whole numbers on a scale of 0 to 14, or you can have decimals anywhere in between. Can't have a negative pH, though. You're at 0 to 14. So if a solution has a pH that is equal to 7, you have a neutral solution, meaning that it is not acidic and it's not basic. It's neutral. So a pH equal to 7 is neutral. Water is pretty much neutral. It tends to be a little bit acidic, like 7.001. That's a little bit acidic, but basic. But most people would say water is neutral. Pure water is neutral. When we put some additives in it, like minerals, it can make it a little bit basic. So pH equal to 7 is neutral. Now, a pH that is greater than 7, that we classify as basic, meaning you have a basic solution. It's composed of basic properties. Hold on, let me fix that there. So if you have a pH that is greater than 7, you have a basic solution. I'm just going to put the 7 there to indicate that. And if you have a pH that is less than 7, you have an acidic solution. So this pH scale gives you an idea of some common things that you might have heard of that are either basic or acidic. So your saliva tends to be a little bit acidic at a pH around 6. Coffee, pure black coffee, is acidic at a 5 scale. Lemon juice, orange juice, that tends to be in the 2 to 3 pH range, meaning it's pretty acidic. Your stomach acid is very acidic, 1, and battery acid is the most acidic you can get. That's sulfuric acid, that's 0. It is very acidic. Meanwhile, your ocean water with the salt in it tends to be around a pH around 8, basic. Baking soda, ammonia, your water that's soapy tends to be very basic, and your bleach and drain cleaners are very basic. So when you're looking at a basic acidic solution, we'll start off with that. Acidic solution, the concentration of hydrogen ions is greater than the concentration of hydroxide ions, those base ions. But if you're looking at something that's basic, it would be the opposite. The hydroxide ion concentration would be greater than the hydrogen ion concentration. And a neutral solution, they would be equal. So I hope this helped you to understand a basic introduction to acids and bases. In a future video, I'll do the types of acids and bases, Arrhenius, Bronsted-Lowry, Lewis, acids and bases. We'll talk about buffers, a lot more with acids and bases, but this was just a brief introduction.